Thanks for joining us. My name's Rod Burns. I work at Coldplay. I've been a strong advocate for SYCL for a few years now. And I guess one of the things I've been involved in over the last few years is what you'll see in the top left corner of the screen, which is SYCL Academy. So myself, along with a bunch of other people, including one of my colleagues, Gordon, who's actually not here today, have put together a set of open source learning materials for SYCL. They're available in a GitHub repo. Anyone can use them. Anyone can propose changes to them. And we've tried to make them as accessible as possible. So today we're experimenting a bit because we've run this tutorial a few times in the past, and we wanted to do something a little bit different and do some different topics as well. So I know that there was a tutorial before this as part of the One API Dev Summit. So we're trying to kind of follow on from that a little bit, just to give you a focus on a few specific topics and maybe talk about some slightly more advanced things as well. So let's see how that goes. Give us some feedback. Be keen to understand how we can do things better. We're going to be doing more tutorials like this in the future, so it's always good to know what works and what doesn't. We do have a fairly short amount of time today, especially compared to the amount of material there is on the SYCL Academy stuff. There's lots and lots of lessons and lots of exercises. So I guess what I'd encourage you to do is make the most of having the tutors available online today in terms of asking questions and having like conversations as well. And I'd encourage you kind of offline to go and look at the SYCL Academy materials and work through them and really understand them a bit better. Hopefully most, if not all of you, have already set up the Intel Dev Cloud from the previous tutorial. It's not totally essential, and there's still going to be time to do that, so don't worry if you haven't. But we thought that would be the kind of lowest path of resistance in terms of getting you hands-on with a bit of code today and making the most progress in the short time that we have. I did want to highlight that whilst we're using DeepC++ today in the Dev Clouds, there's a bunch of other SYCL implementations, and I think that'll be covered in the introduction. But yeah, there are lots of different options for you to use, and today we're just choosing one of those. So as I say, the support can happen on the Slack channel today. I'll leave it to individual speakers if they're happy for people to either use the Slack channel or even to kind of ask questions in person and live on the Zoom chat. So please, whoever's doing the presentations, let you know what your preference is. I know that's different for different people. But yeah, I guess it'd be good to do a little introduction for the different tutors that we have into the session today, and they can tell you a bit about themselves. So why don't we start with Axel? We'll go left to right. Are you there, Axel?
Hi, everybody. My name is Axel Alpay. I work for Heidelberg University. I am mainly known for leading the SYCL implementation of SYCL, and I'm also a member of the Kernel SYCL working group.
Thanks, Axel. That's great. And we have Igor with us as well from Intel.
Yeah. Hi, my name is Igor. I'm a technical consulting engineer, so my primary focus is on Intel compilers, including C++ version and obviously SYCL compiler. Yeah, and I'm usually also working on some kind of optimization tasks, like performance optimizations and so on.
Excellent. Peter, are you there? Just checking that he's made it. Oh yeah, you are there. Peter, are you able to tell us a bit about yourself? Okay, maybe there's
Hi.
Oh,
yeah.
okay.
Sorry, just a little bit of technical issue.
Yes.
Yeah. Hi. I'm Peter. I work for Coldplay, and I'm the product owner for Compute CPP. So that mostly means managing a team to develop the SYCL implementation and also help in the SYCL working group.
Cool. Thanks. And Ronan's cunningly put AMD at the start of his name, so it appears right near the top of the Zoom participants list. So tell us a bit about yourself, Ronan.
Hello, so I'm Ronan Keriel and I work at AMD on SYCL, and I'm also the spec editor for the SYCL specification. Voilà.
Cool, thanks. So yeah, as you can see, we've got lots of experienced people, both spec editors and SYCL implementers, and also optimization experts as well. So a very good group of people here today. I'll just run through quickly the schedule of the way we're hoping things are going to go today. So we're going to start off with a short introduction to SYCL, and Axel's going to cover that. Then after that, there'll be a bit of time for questions, but also for you to go away and make sure that you've got your development environment set up and that you can compile things in the dev cloud. And yeah, after that, we're going to move on to some different topics. It kind of jumps from intro to your first kernel, then a bit about memory management that Peter's going to cover. That is a very important thing to know. And then after the break, we're going to cover some slightly more advanced topics in a bit further detail. ND range kernels, which is, I think Ben covered a bit about that in the previous tutorial when I was watching, but this is going to go into a bit more detail about how you might use that. And then there's a hands-on exercise for you to try to implement an ND range kernel, which is good. And then the last session is going to be a bit more free form in terms of there is a presentation on this image convolution, and Peter's hopefully going to talk a bit more about the actual code and I suppose walk through some of the different SYCL syntax implementation details and techniques that you can use. Cool. Okay, so let me pass over to Axel to kick things off. Thanks for joining us, Axel, and yeah, I'll hand over to you.
All right, thank you. So let me just share my screen. All right. So in the first presentation, as Rod said, it's just going to be a broad introduction to give you some general idea about what SYCL is. So we're going to be learning about the SYCL specification, about the different implementations that exist. We're going to learn about what makes up a common SYCL implementation, how it works. We're going to learn about how SYCL implementations commonly process source files and compile them. And we're going to talk about where to find useful resources for SYCL. So SYCL is a high-level single source standard C++ programming model that can target a wide range of heterogeneous platforms. And I know that this sentence is quite a mouthful, so in the couple of future slides, we're going to dissect that sentence a bit and focus on the individual aspects. So don't mind if you don't quite grasp already what all that means. So to give you a first impression, this is a SYCL example code, and if you have done the previous tutorial, then maybe this might already be familiar. But if not, then don't worry, because those elements will also be explained in more depth in coming parts of the tutorial. But so the general idea, so it's pure C++, so that there are no additional pragmas or additional attributes required. So you can just express parallelism with regular C++, and you can define your queue, and then you can define some buffers to manage data. Then you can submit some work, and then you can also have some code that's actually executed on your device that you're targeting. It's all C++ and it looks like regular C++. So SYCL extends C++ in two key ways. There's device discovery, so you can ask SYCL what devices are there. And there's device control, so you can submit kernels, you can manage memory, and so on. SYCL is modern C++, and it's also an open multi-vendor and multi-architecture solution. So let's first focus on that single source aspect. So it's a single source high-level standard C++ programming model. What that means is that you can write both your host and your device code in the same C++ source file, and they're going to be parsed together by your compiler. That means, for example, that you can have templated kernels. And in common implementations, this requires two compilation passes, one for the host side and one for the device side. So you would have your device compiler that first analyzes your code and detects kernels, extracts those, compiles those for your device to some intermediate representation or some machine code. And then you'd also have your host compiler, which compiles your application. And then if you call a submission function to your SYCL queue, this would then call into the SYCL runtime, which would then talk to some backend such as OpenCL and feed the compiled device binary that has been generated by the device compiler into the runtime. And then all of this can run on the CPU, which controls the execution, but it will also be able to offload work to your accelerator. It's also a high-level model, and that means that it provides high-level abstractions over common boilerplate code, such as platform selection or device selection, buffer creation and data movement, kernel function compilation. So if you're used to OpenCL, then you might know that in OpenCL you generally need to compile your kernels manually. You don't need to do that in SYCL. It will also take care of dependency management and scheduling. And it's standard C++. So as I had already mentioned, you don't need any additional attributes or pragmas and other mechanisms. So you can just write parallel for, give it some lambda function. So you're expressing C++ with regular C++ mechanisms. And it's based on C++ 17 and yeah, pure C++. And it can target a wide range of heterogeneous platforms. So the SYCL implementation generally consists of a number of different backends, and then SYCL can run on top of any device supported by a particular backend. And that allows it to target things like CPUs, but also GPUs, APUs, other accelerators, FPGAs, DSPs, and so on. And it has been designed to sit on top of a variety of backends. So this previous SYCL versions were mainly focused on OpenCL, but that's no longer true. So current SYCL implementations support backends such as OpenCL, CUDA, HIP, OpenMP, and others. The current SYCL specification is SYCL 2020, which was released publicly released in early 2021. And before that, there was mainly SYCL 1.1, which is the older version of the specification. There are multiple SYCL implementations available that target different backends and different devices. There are three implementations that most people are using, and that is DPC++, which is part of the One API project and mainly focuses on Intel devices, but also has support for CUDA GPUs and also recently AMD GPUs, which is still lacking here. Then there's Compute CPP from CodePlay, which supports mainly OpenCL backends. Then there's SYCL for NVIDIA and AMD GPUs and also CPUs. And also we have experimental support for Intel hardware. And then there are other SYCL implementations such as TriSYCL or NeoSYCL, and then more research implementations that are not listed here, such as SYCLcon and others. So there's really a growing SYCL implementation ecosystem. And there's a wide range of implementations to choose from. And it's highly likely that whatever your needs are, there's some implementation that's going to suit your needs. So what does a SYCL implementation look like? So there's a SYCL interface. This is the C++ library that you're calling into when you're writing a SQL code. It's a C++ template library, and that's what you're going to use if you access the SQL features. And the same interface is used both for the host and the device side. The host is generally the CPU, and that's what's used to dispatch the kernels. And the device is what we offload the kernels to for execution. And that might be something like a GPU. It could also be the CPU if you want to run your kernels on a CPU, but it could also be a GPU or an FPGA or something like that. Then there's the SQL Runtime Library, and the SQL Runtime Library, well, it does all the runtime things. So it schedules the work and manages execution. It loads kernels, tracks data dependencies, and so on and so forth. There used to be a host device in SYCL 1.1. There's no more a dedicated host device in SYCL 2020. The host device used to be an emulated, kind of emulated C++ backend to run on the host, but still SYCL 2020 implementations generally offer a CPU device, which might be very convenient for debugging, for example, because chances are that things might be easier to debug there. But still, if you're running into some device-specific issues, then it's still an important, then it can still be very important to actually debug on the actual device on which you're running on. Then there's a backend interface, which is what the SYCL runtime then calls into to communicate with a particular backend and actually make things run on a particular backend. Many implementations provide OpenCL backends, but as I had mentioned, there are also other backends that some implementations use, and that backend interface could, for example, also talk to CUDA or OpenMP or something else. Then there's generally some kind of compiler component, a device compiler, and that is a C++ compiler which parses your code and identifies the SYCL kernels, extracts those kernels together with all the functions that they're invoking, with all the code that they need, and then compiles them for your particular targeted device to some intermediate representation or some actual machine code. So that intermediate representation could be something like SPIR or SPIR-V or PTX or something else. And some implementations are library only. So this is another implementation choice that's allowed by the SYCL implementation. If you have a library only SYCL implementation, then the SYCL implementation acts as a library for a third-party compiler, in which case they do not need to ship their own device compiler. And that third-party compiler might typically, for example, target the host then. And then it would be just like a regular C++ library that runs on the CPU. So let's now talk about how SYCL compiles things. And first, let's quickly recap how C++ compiles things. So in C++, you have your C++ source file that gets then fed into your regular C++ CPU compiler. You get a CPU object out of that. Then this is linked, and from your linker, you get your executable machine code binary, and you can then execute this on your CPU. Now, if you want to offload some work to some other accelerator, something like a GPU, for example, then how do we actually extend this compilation process so that things can also run on the GPU? So in this case, we not only have our regular C++ source code, we also have in the source file, we have parts that are intended to run on the device, our kernels. And these are commonly expressed in SYCL as either function objects or lambda expressions, and are then submitted using specific SYCL APIs such as Parallel4. So the device compiler also parses your source file and detects those kernels and generates some kind of IR, such as SPIR, SPIR-V, PTX, or machine code for a specific architecture from that actually contains the code for your kernels. Then all of this is kind of mangled together, form some kind of binary that can run on the host, but that has the code that would execute on device embedded inside of it. And that means that you can just run your resulting binary as a regular C++ binary and execute it. But inside that binary, there's the compiled kernels, and that can then be executed by the SYCL runtime on a particular device, such as a GPU. This particular model is the multi-compiler compilation model, and it allows the host compiler, which might be MSVC or Clang or GCC or something else, to be independent of the SYCL device compiler. Alternatively, you can also have a single compiler compilation model where all of that is handled by the same compiler, and that has that makes you less flexible with respect to which compilers you can use, but it allows certain things that might be more cumbersome otherwise. So there are advantages and disadvantages to both designs. So where to get started with SYCL? So there's the SYCL.tech hub, and you can find out all about the implementations, tutorials, news, current videos about SYCL there. There's also a SYCL book, and you can find information on that also there. For the latest specification, you can always go to the Kronos website where you can access them either as a PDF or as an HTML website. And of course, you can also just check with your implementation for documentation that might be shipping with that implementation. All right, that's it for the introduction. If we have some time, then we can take some questions now, or you can leave them in the Slack channel.
Well, thanks, Axel. I guess it's worth pointing out that I suppose the only difference between using the different implementations of SYCL is often just a build configuration step rather than anything else. The same code runs across the different implementations. That's really the whole point. So yeah, so that's why we can produce the SYCL Academy materials and run them with any of the implementations. All right, what's the question? Do implementations allow you to profile only the host portion of the code? I assume that is possible with a profiler that's a standard profiler for the CPU, I would imagine.
Yeah, in the end, a SYCL application on the host side acts like a regular C++ application, so you can apply a regular C++ profiling tools or system profiling tools.
I guess from a profiling perspective as well, the manufacturer of your processor's profiler is almost certainly likely to work alongside SYCL. For example, if you're using an NVIDIA GPU, you can use the NSYS and what's it called? NV Compute profilers with both HipSYCL and the CUDA backend for deep C++ as well.
Yeah, so generally, since SYCL is designed to sit on top of other backends such as CUDA or OpenCL, you can use whatever tooling you have for that particular backend. So if you have an OpenCL-based implementation, you can use whatever works with OpenCL. For a CUDA-based SYCL implementation, you can use NVIDIA's tooling. For HIP-based implementation, you can use AMD's tooling, and so on and so forth.
Yeah.
And in some implementation, you can, like, let's say, some implementation of backends like level 0, there are some APIs which are dedicated for profiling. So you can even write your own tracer or reuse some existing utilities available on GitHub and do profiling yourself. So it really depends on the backend, as folks said.
Yeah, cool. And I think, well, Peter probably knows more. I think there's some tracer APIs in Compute CPP as well, which have been added. So yeah, there's quite a lot of different options. The second bit, I wasn't really sure. Instrumentation may tag device code or glue code, and I'm not sure what you mean exactly by that. but yeah, maybe we can continue the conversation on the Slack channel. Okay, so first thing to do, let me share. So the first thing to do in this part of the tutorial is, I'm trying to move this out of the way. So in the Slack channel, I'll also put it in the Zoom channel as well. The repo on the correct branch lives here, and the git clone command is this to get the right branch, which you can copy and paste. I've put that in the Slack channel here as well. This is the clone command there. So I would encourage you to follow along. What you can do is go to the dev clouds. Oh, this is where I need to sign in. All right, so this, I think it's this one. Okay. So you can either register or sign in, and instructions are all listed on the README of this repository. So what you can do is start working through this bit, which is what I'm doing here. And so these, okay, I'm going to follow my own instructions. So we go to this page and then scroll to the bottom, this is probably the easiest way to do it. There's different ways to launch it, as you may have learned in the previous session. But on that, so there's a page linked here. If you're logged in, go to that page, scroll right to the bottom, and then you can connect with the Jupyter Notebook. It takes a little while to start up. How's everyone getting on? Okay. So from here, you can open just a terminal, which is the easiest thing to do. And you can use this clone command to get the repository in your dev cloud instance. Oh, shouldn't happen to you. Take a little while to pull down all the different components and stuff like that. Yeah. There's a question while we're waiting. Stuff. Maybe someone can help in the chat. Which SYCL compiler has host and device codes compiled separately using two compilers?
I think finally it really depends on for which target device you are compiling, right? So
Yeah.
Anyway, if you consider a target device as a GPU, it's impossible to compile it with a single compiler because you need a device compiler, GPU compiler, and you need a host compiler, which is a CPU compiler, right? But if you're targeting, let's say, CPU as a device, and you don't use OpenCL backend, so you have in the implementation of a vendor, right? You have a support for this native generation for device code. Then theoretically it's doable. I think in DPC++ we had it when the host selector was still in SYCL 1.2 standard. I think now it should be also supported under this debuggable aspect feature of a device, right? Because it should guarantee that the device is available even if OpenCL is not installed. But at this moment, I would say that this implementation, at least in DPC++, this implementation is not optimal because the focus is to support real acceleration, right, to GPU. And this always considered as more debuggability feature to natively run both kernels and host code on the same CPU.
Yeah, I noticed Axel's put a response in about how SYCL does it as well. We're using, I think there's a presentation at IWOCL about this, in fact, using a single compiler with the NVC++ backend. So it might be worth, Zamming, you might be worth looking out for Axel's presentation tomorrow, I guess.
Yeah, in that presentation, we also discussed some of those implementation options in more detail and how they impact SYCL implementations. So if you're interested in how those different models and SYCL implementations work, then that might be a good place.
Well, thank you for your answers. Yeah, they are helpful for me to understanding more about your compilers.
Yeah, note one maybe also interesting for you that you can actually replace a host compiler. So let's say if you want with DPC++ by some reason to use GCC for the host part, you theoretically can do this, but you will need to do some kind of hints, right? So since it's based on CLang, you can add minus double dash or triple dash command, get the list of commands executed, and a bit replace some of the commands. So a lot of stuff is doable, and yeah.
Can I ask a question about the performance? For example, if we are trying to write something like unified code, what I mean by that, if we're creating a queue without specifying the GPU selector or default selector, so we will use just default constructor. And then afterwards, we will be able to run the code using the flag, I don't remember exactly, SYCL device filter, something like that. So we'll be able to run our code on CPU as well on the GPU and so on. So will be any performance degradation if comparing to the hard-coded GPU selector, for example, in our code, or it will be absolutely the same?
Actually, it doesn't matter if it is a default constructor you used or you used explicitly a GPU selector. It doesn't affect the performance. The performance will be affected by the code itself you are writing in the kernels, right? So again, if you want more fine-tuned code for each architecture, it's a better option to fine-tune it in the code, right? Based on the device. In principle, with default selector, functional portability is guaranteed, right? So that you will be able to run this code on different devices, sometimes including FPGA. But it's very hard to guarantee performance portability in this case. If you will manually write your code in a way that you have different paths for GPU, for CPU, for FPGA, it will obviously give you better performance if you're doing fine-tuning, because architectures are in principle under the hood quite different, and it will require some fine-tuning from your side.
Also, one thing to keep in mind is that the SYCL device filter is really a DPC++ thing. So this is not guaranteed to be available in every SYCL implementation. Or let's say different SYCL implementations have different ways of doing this. So if you want your code to be portable across SYCL implementations and be standard SYCL, then the only way you have to actually make a decision on which device you want to run on is to use the C++ interfaces of SYCL and make a decision based on that in your code.
Okay, clear. Thank you very much.
No, thanks. Okay, so let's move on to the next section, which will be presented by Igor, which is introducing, I suppose, how kernels are written and invoked. So we'll do that, and then after that we can see if everybody's got set up on the dev cloud, and then run or compile and run your first kernel. But pass over to Igor. Thanks, Igor.
Can you hear me? Yeah, should be.
Yeah, we can hear you. Yeah.
Okay, and the slides are visible too, right? Okay,
Yeah,
great.
yeah.
So yeah, and this part we are going to talk more about queues itself, right? Ways how to submit some work to the queues, some basic stuffs about what is common groups, why we need common groups, how to define kernels inside common groups, and so on. But also we will talk briefly about restrictions on the kernel functions. So sometimes there is quite common confusion that there is a statement that it's like SYCL is based on C++17, right? So that's why I see that developers expect to be possible to use C++17 features everywhere, right, including device code, but that's not really true. So there are some limitations on the kernel functions and the device code, and we will briefly talk about it. And one more hint, we will talk about streams and how to print actually some data from your kernel functions to a console, and sometimes it's the most powerful thing to debug your code. So what is the queue? I would say that it's a basic principle in SYCL how to link to device, right? So all work in your SYCL code is submitted via commands to a queue, and the queue is always associated with some device. The device may be different actually, and you can use a different constructor for the queue. In the basic case, it's usually a default constructor, and we already had a question on that, but you always have a way to construct a queue dedicated for some specific device. It may be a queue constructed with a GPU selector, it can be a queue constructed for CPU, and so on. So you can even create your own selector by writing your own selector class. So the most straightforward way is to use the default, obviously, nothing required, just create a queue object. And in this case, the SQL runtime will choose a device for you. And it's quite interesting that there will be some kind of a cost model right here, because the runtime may try to pick up the most performant device for you, and it should score all available devices on your system. And let's say in DPC++ implementation, integrated graphics will be preferred versus CPU. And if you have a machine with integrated graphics, CPU, and discrete graphics, then the discrete graphics will be scored as the highest. But the thing is that you can actually override this behavior by writing your own device selector. In SYCL in principle, and there will be a dedicated talk for this part, but in SYCL in principle there are two major models for managing data, right? So you can follow the buffer accessor model, where you're wrapping your data, you're putting into the additional buffer container, and you're using accessors to access this data inside the kernels. Or you're using unified shared memory, which is a feature of SYCL 2020 standard, became a feature of 2020 standard. And as I said, there will be a more specific talk on that. For now, we are going to be more focused on the following examples on the buffer accessor model. And yeah, actually, where the way or the model you are choosing for managing your data in your application, it actually affects how you enqueue the kernel functions. And I will show a few examples on that. In the buffer accessor model, all commands should be enqueued via the command groups. In the USM model, you can avoid doing it because you don't need to create accessors. So a command group actually represents a series of commands which you are going to execute on the device, and these commands may consist of invocation of a kernel function on the device, right? It consists of a memory copy back and forth to and from the device, and you can also wait on other commands to complete, right? So you always need to submit the command group to the queue. So there is a submit function, right? And the argument is a reference to the command group handler. And actually, this command group is constructed inside the function. So the submit function takes a command group function and it acts as a factory for composing the group itself. And it creates this command group handler and passes it to the command group function. Then the handler composes the command group itself. So as a code example, it looks like this. So you constructed some queue. Yeah, you can call a queue GPU queue like in this example, and use a default constructor for it. And then at runtime, you can rely on the runtime to pick up the GPU. So here it may be a bit confusing because to be sure that it's GPU queue, you need to create it explicitly with the GPU selector. Otherwise, with default constructor at runtime, it may even pick up a CPU. And it's a good practice actually in your application to print what's the device on which you are running. Or in some implementation, there are traces or debug logs which will show you where you're running. So you have a queue constructed and you are calling a submit method of this queue, and an argument. First argument is a C++ function objects, which takes a reference to a command group handler. This argument may be a lambda expression, like in this example, or it may be a class with a function call operator. This body of this function, it represents the command group function, and in SQL there are three scopes, right? Your host scope or application scope. There is a command group scope, and there is also a kernel or device code scope, right? And depending on in which scope you are, you may have some additional features or you may have some limitations apply. Note that this command group function and is processed exactly once, right? So it's not iterative calls of these statements. And at this point, all the commands and requirements declared inside the command group function are processed to produce a command group. Quite important note is that the command group is submitted asynchronously to the scheduler, which means at this point we don't stop the execution of a host code, right? So we are not waiting until the execution on the device is finished. We keep executing the host code until we are using some spatial features to synchronize and to stop execution and to make this call actually synchronous, right? Again, implicitly the queue will not wait, and if you want it to wait for other commands to complete, then the submit method actually returns an event And there are multiple ways how you can synchronize in SQL via these events. So in this simplest example, the event is returned and we are calling the wait function on this event, right? What you also can do is you can call a wait member function from the queue itself, and then the behavior is quite different, right? Because wait on this event will wait for completion of all kernels, right, executed inside this common group only. So only this common group completion we will wait here. But if you call GPU queue dot wait, then in that case you're waiting for all submitted common groups and kernels to this specific queue, and it will actually cost you a lot depending on your goals, right? So here we call wait on the event, right, to immediately wait for completion of this specific code. Obviously, there are other ways to do this. I don't think we'll go into more details today on the other ways, but yeah, you can find on the GitHub project in our branches, you can find a lot of information on that. So as I said, the scheduling is happening under the hood. So once we submit and submit a common group, so a common group is created, right? It is submitted to the scheduler, and the scheduler then executes the commons group on the target device, but it cares about dependencies and some requirements, right? So there is a scheduler, there is actually a graph which is built under the hood, and a more submit operations you are doing to the queue, and more nodes to this common this graph are added, and then the scheduler scheduling the execution of device codes based on dependencies between nodes of this graph. So obviously it should be a mechanism to express these dependencies, right? Data dependencies between kernels, we will talk about it. But one more note, that the same scheduler is used for all the queues. So that's how the sharing of a dependency information is possible, right? So the scheduler actually knows about it. In DP++ implementation, we even have an option to print the graph which is built itself and get this information at runtime. So SQL kernel functions are defined using one of the kernel function invoke API. So in this example, we are using a single task invoke API, right? And it is provided by the handler. So you can see that we are calling a member function of a handler. But there are others. So this is quite simple example. So I would say the most common is parallel for. Single task means that we execute the kernel code only once on one work item. And note the important, I think when developers start to use SQL, they're also missing the important limitation that is that there can only be one SQL kernel function common in a common group. So you can not call single task and then a parallel for or two single tasks in the same common group. The kernel function invoke API take a function object, so it's the same way like we were passing the argument to a submit method, right? To the single task, we also passing a lambda or a class with a function called operator. And this is actually the entry point to the code that is compiled to be executed on the device. And this is kernel code scope, right? So here it was a common group scope, and here we have a kernel code scope. And there will be limitations for the features which you can use inside here. We will talk on it. Note that there may be different parameters which you can pass to the single task of these kernel invoke APIs to describe the iteration space, right? So different kernel invoke APIs can expect different arguments to be passed. In this example, since we are going to invoke it and execute only once, there are no additional arguments and parameters passed here. But in case of parallel for usage, you need to specify range or any range, somehow identify the work item, and it will be explained in the upcoming parts by my colleagues. Note that sometimes, depending on the implementation, you need to name the kernel function, like in this example, right? Let's say in accordance with SQL 2020 standard, it is allowed that this lambda will be unnamed, right? But not all implementations at this moment support that. So for example, in DPC++, you can avoid writing the kernel name, but my personal view here is that it may be quite useful, because if you don't write explicitly the kernel name, then while profiling your application with, let's say, vTune or any other profiler, the name of the kernel will be not representative, right? Because in that case, the compiler will generate the kernel name for you, and it may be some kind of set of symbols which you know, don't bring give you a clue what this kernel is. So I would say that giving a name is quite useful. So there are a few of kernel functions rules itself, right? And first of all, as we said, it must be defined using a C++ lambda or function object, right? We cannot use a function pointer or function from a standard library. Actually, there may be some extensions in available from different vendors where you can do this, but it's not in the standard, right? Must always capture or store members by value. SQL kernel functions declared with a lambda must be named using a forward declarable C++ type, which is quite clear. So you first need to declare this type and then to use it. And also, you cannot have two kernels with the same name, right? So you need to follow the standard C++ rules on that. Now the limitations about kernel functions, right? So inside the kernel scope, you cannot do the dynamic allocation. The dynamic polymorphism is not supported, no function pointers, and no recursions. No exceptions as well inside the kernel function. So far, we were talking more about the way how to call a single task, right, with a lambda, right? Let's have an example where we can call it via the class with a function operator implemented. So in this case, if we have some class and we do have a function operator, you can actually use it and invoke single task method or parallel for methods and do it in this way. So this is an example. So in this case, you no longer need to name the SQL kernel, right? Because you already named your class and you're passing this class as an argument to the single task. Now quite a useful way how to print something to the console from the device code, quite similar to what you're doing with a standard cout statement. So note that the stream is actually a buffered output stream. So the output may not appear until the kernel functions is complete. and it's quite often used for debugging purposes, but it's better to avoid adding it to some performance critical code since it can slow down the execution, obviously. But for debugging, it's great. It must be constructed in the common group function, and the handler is required to do that, since it's the last argument is a reference. And you also need to pass two arguments. So one is a buffer size. So it's setting the total size of a buffer that will store the text, and the second one is actually work item buffer size, and it represents the cache that each invocation of a kernel function has. So this is an example of how you can use a SQL stream inside, and you can see that it's constructed here in the command group scope. So we're creating a stream with a buffer size of 1024, and the work item size is 128, and we are using a header. And this is a very simple example of how you can use this constructed stream inside your kernel and print some hello world to the console. So I think that's it. I now want to show you a lab exercise which we have.
Good. Can I have a short question?
Yeah,
before
sure.
you proceed? I mean, about the lambda capturing, because I can see in the submitting to the queue, we are using capturing by reference. And when we are submitting to the kernel code, we are using always by value.
Yeah.
Are there some restriction with the lambda capturing within this context?
Yeah, this is a strict limitation how to pass it to the kernel itself. I think it's coming, maybe colleagues may help me, but it's historically coming from the time that it's a device code, right? So you cannot pass it by reference. So originally there was no USM right there, so there was only one way to copy the data to the device code, to the device. So that's a limitation set by the standard itself, and it's critical. You cannot pass it by reference.
Even using unified shared memory is not possible at the moment, right?
With unified shared memory, it will be a different, let's say, way how you can invoke your kernels. So in that case, you actually not always need to construct a common group scope, common group explicitly. So there is a feature to do it with unified shared memory in the other way. So in that case, you really use a unified shared memory, right? You can operate with a pointer, and this pointer address will be same for host and device side. But this will be discussed in the upcoming sections, I believe, the USM model, and I think we'll answer your question partially.
Okay, thank you very much. And USM is a feature of SYCL 2020, right?
Yeah, it's a feature of 2020, and I believe it's already supported by all the vendors, at least SYCL, Compute CPP, and BPC++ does support USM quite well.
Thank you very much.
Okay, so just maybe few pointers. So it's really simple to get an access to the dev cloud. So all you need to do is to register for this access, and it requires to fill a few fields, and you should get your account. So once you get it, please go to this Get Started page, and what you can do is actually connect. So there are multiple ways how to connect to the dev cloud. And DevCloud is the resource Intel is set up for developers to easily access Intel hardware and software. So it has one API and DPC++ pre-installed, so it's quite convenient for us today to use it for our lab exercises. There are two ways how to connect via SSH, so you can configure your PuTTY or whatever to connect via SSH, or you can sign in using this Jupyter notebook interface with Jupyter Lab. I actually prefer this way. It's very simple. So if you click here, so after you sign in, if you click here, you will able to launch this lab, and then it will open you this page, which usually shows you how the submission of jobs on the Dev Cloud works for you, right?
And there are no other ways how to connect it without the Intel account, right? Because I have been registered, but for now 1 hour ago, but I still didn't get the confirmation code to my email. I resent it twice, but still nothing, even in the spam, in the junk folder.
Yeah, that's very strange because I was doing it with external mail just yesterday, and I got it like immediately. So it shouldn't be this kind of problem. I hope it's not some kind of a temporary out of service stuff. But yeah, if it will continue, yeah, just ping me. Let's see if for hours there is the same issue. Then I will
I'll try to register with the other email, with the Gmail, because I tried to use my company email.
No, actually, I registered with the Gmail or with Hotmail, and it worked very smoothly. So should work. Let's see if this problem stays. I will work with you offline and help to solve this. Shouldn't be an issue. So yeah, unfortunately, without account, you will be not able to log in because you're getting this unique unique user ID to connect. And there is a terminal you can open here, so you can see that this is my username. Right? So once you registered, you're getting this username. And so on the Dev Cloud, you are always logging in to the login node, which means you can still compile. So there is a DPC++ installed here and one API, but it's login node, right? If you want to submit some job to be executing on the nodes, then you need to follow a special syntax to do this. Or my favorite thing is to allocate some node in the interactive mode. So I'm quite often use this command, which is saying, please allocate me the node in capital I here means interactive mode, right? And I'm looking for the nodes with GPUs, like it may be integrated GPU, it may be discrete GPU, doesn't matter, but I'm looking for some node to be allocated interactively for me. So once it is done, I can get access directly. You see this is the different node and 180, while the login node was 009. So here, everything is installed as well, but we can compile and run right on the node, on the compute node. That's what I recommend to do. So just cloning the GitHub repository with exercises using this command, right? And since I already did it, I'm not going to duplicate. And then changing the directory to SYCL Academy and to code exercises subfolder. So, and there are 4 different exercises for you today. So now we are in exercise 2 step. So let's go there, and you can see that there is a README document explaining what you expect it to do. So it's very simple. We expect you just to create a queue, to select some device if you want, right? To print a device version, a driver version, and to build it. Right? You can also print something from the kernel. There is prepared for you solution code, right? Which is doing quite simple stuff, creating the queue, printing the device info, or getting the device info and printing it there. But you can also do as you wish depending on the time you have.
Yeah.
And
so
yep.
So I was going to add the source file also has in the comments the kind of some code hints as well if you don't want to look at the solution necessarily and want to go through it. So this one I think contains most of the things that you need there, but I guess it helps you to work through that. So there's that source. The other thing was an add, there's a couple of scripts in there that help with the job submission. I think that run.sh, if you open that, Igor, has like the commands that you would normally run. So you can just run that, or you can also run that queue one, which does it in interactive mode. If you wanted to show that. Yeah.
One important note is that in interactive mode, we can compile here directly, right? Like this, and then execute, and it will be executed on the same node where we are, right?
Yeah, that's true.
But the thing is that to measure the performance critical stuff, right? It's better to use the queue submission through the regular scheduling mechanism, so that it will be properly scheduled and executed with a full utilization of resources on some node. So that's why for this basic stuff, it's obviously not required to do, but so you can just run it and that's it. And it will print you the chosen device, right? Since we implemented this in this solution CPP. But the other way to do it, if you want to submit it on some stuff, so there is a nice script prepared, which is called queue. It's a script, and you can pass the script you want to run. So in that case, the job will be submitted to the dev cloud, you see, and we are waiting until it's going through the scheduler of a login node and finally submitted on some random node which is qualifying for our requirement which we set in this script run.sh. So again, for me it's more interactive to get the node directly, right, and to compile it. The other option is to use it via scripts and to schedule it to be executing by login node. And you can see in that case, we were waiting for progress, and finally the job was also executed on the other node, on this node. Oh no, it's not saying here the node. So these are two ways how you can do it. I think I put to a chat the comment.
If you run it on the same node, is that a GPU or is that a CPU that's running on, or is it, or both cases?
Yeah, actually, when I was getting the node, right, I specified that I want a GPU node to be allocated, right?
Right, I see.
So that's why it's running. So when I was running this command, I thought I put it to the chat. Let me do it again. So if you run this command, then you're getting the interactive mode, and you're explicitly saying I want the node with GPU. So that's why when I'm running the application on this node, it's running on GPU, right? But you can play with it because there is a SQL device filter in DPC++ implementation. I would not recommend to use it at this moment. I would recommend to play with the queue constructors and to select CPU selector, for example. So to try to play a bit. So this is the intention of exercise, right? To play a bit, to give you some freedom to try a few stuffs and some stuff, and then we can come back, right? I think that's it from my side, and feel free to ping on the Slack or in the chat.
Thanks, Igor. Yeah, give us some feedback about how you're getting on. Helps with encouraging each other if we know that you're managing to get through two things. So yeah, so let us know, and we'll let people spend a bit of time playing around. We also have the ability to set up breakout rooms, which may not really be needed for this one because it's fairly straightforward. But if you are having problems with setup or even registration, and we can try and help to diagnose some of that. So give us a message, and yeah, we can set up a breakout room where we can meet you one-to-one if that helps. But let's give you a bit of time to work on that, and then we'll come back and move on to the next section, which will be about memory management stuff. Pick this up. Schedule's a little bit rough. You don't want to be too constrained by the schedule if there's questions coming in and stuff like that. So, okay. So,
I have a general question. We have several great implementations of SQL, and I can see that some of them have different functionalities, and they all have similar functionalities. Which one to choose? How to decide? Is there any comparison between the SQL implementations or something like that?
I think there are a couple of sites here, right? So first of all, I would say that there is no implementation available right now which has all the SQL 2020 features, right? So there is no fully conformant compiler at this moment, unfortunately, and this is one goal, and we all together, I think, working in the direction to get to a point where all implementations support SQL 2020. This is one point which is quite important, and there are actually links to the pages listing which features supported by which implementation, which can be useful, but the second part is more, I think, about the efficiency of a specific implementation, and I guess it's hard to speculate because it's very dependent on which device you're going to target, right? So it's very hard to say what's your final goal, right? Let's say Compute CPP has a great support for some devices Intel doesn't have, or let's say HipSQL is great with AMD support. So there are strong advantages on each implementation. It's very hard to suggest something specifically. I think it's very dependent on your use case, right?
But what if the backend is supported by several implementations? How to choose, for example, Intel CPUs, of course, I would think that if I need Intel, so I have to choose DPC because it's an Intel implementation, just logically. But the Intel CPUs are supported by other implementations.
I think the great thing of SQL itself is that you have a choice, right? So finally, if you write your SQL conformant code, you can finally recompile with any implementation and decide what's working for you. I would say there are different stories, like let's say Codeplay, even on their page, pointing that to get better support for NVIDIA hardware, it's better to use CUDA backend and DPC++ just because it's more efficient, right? The implementation is better because it's based on OpenCL and Compute CPP, which is a bit slow, right? And with CUDA backend and DPC++, it's fast implementation. So there are pros and cons here and there, but again, finally, what is great is that you have a choice to try everything and decide based on your demand what you really need. And then I hope that, again, as soon as possible, we'll reach the milestone where they have a full support for SQL 2020. Then you will be really, able to migrate from one implementation to the other and compile it.
So the perfect choice, how to find out, will be the Kronos website. Because almost every implementation is specified there, so I can read just the documentation, and depending on my needs, I can choose something, right?
So there's information on
the
there's information on the Kronos website about implementations that are available. There's also, I think, the same information on places like Cyclotech. I think one of the best places when you're talking about choice and performance and stuff like that, I think the IWOCL SYCLcon conference is probably one of the best places to go to see some of those comparisons. And it also depends, I suppose, on the workload that you have. the target hardware that you have and stuff like that. But there's quite a lot of talks this year, well, and in previous years, on like performance on different hardware and comparing different implementations. But I guess, as Igor says, you know, if you are using an implementation and decide that the performance might be better with another one, then there's nothing to stop you from switching over, because the code shouldn't be, well, won't be any different. I don't know if Ronan was going to say something. He's just popped up.
Yeah. So I think that's a very good question, and there is no simple answer. As Igor said, the great news is that you have a different implementation, and then you can try, because probably for your specific problem, there is one that will provide you better performance or better user experience. And even some implementation, even if they are conformant at some point, might have some extensions that are useful for you and so on. So it's like, choosing nowadays C++ compilers, you try or you mix and match, but you have the choice, so that's the great news. But there is no, like in any choice, there is no obvious cost metric, or so it's up to you to try, but at least you can try.
Cool, thanks. So has anyone managed to get their SQL code working? Should have brought some prizes or something for that. Does anyone want to have a bit more time on getting things set up? I guess let us know in the Slack or in the chat if you want to have a bit more time. Okay. I guess we have quite a bit of stuff to get through, so let's move on to the next section, where Peter is going to be presenting on different types of memory management that you can use in SYCL. Are you ready, Peter?
Oh, hello. There we go.
We can hear you. Yeah, perfect.
There we go. Okay. I'll just start sharing my screen. There we go. Okay. This.
Yeah, we can see that. Right. Perfect.
Excellent. Okay, so in this section, we're going to focus on managing data, as Igor alluded to in his presentation. And we'll learn about like the buffer accessor model and also the USM model for managing the data, how to use these, and how to use the data in a kernel function, and also how to synchronize data. What's important to note here is, as mentioned, that there are two main models here that you can use, either the buffer accessor model or the USM, the unified shared memory model. And what you choose can have an effect on how you enqueue your kernel functions. So let's start with buffers and accessors. So this was originally already in SYCL 1.2.1. And the basic idea here is that you separate the storage and the access of the data. So the SYCL buffer manages the data across the host and any number of devices and actually stores the data, whereas the SYCL accessor requests access to this data from the buffer, either on the host device or, well, either on the host or any device for a specific SYCL kernel function. So this is the part of the accessor that's where you can request access, but inside the kernel, they also provide access. So you can use them kind of like pointers inside the SYCL kernel function. So you declare them in host code, but then they're captured into the SYCL kernel. So what you can do, for example, with buffers is that you can create a buffer using a pointer to host memory. And then for the lifetime of the buffer, this memory is owned by the SYCL runtime. When you create a buffer, it will not allocate or copy to any device because it's not associated with any device yet. But it will do so when data is needed, when a kernel requests access to this data. Yeah, so for that, you create an accessor to request the access to the data, and there are different ways that you can do this. When you create the accessor, you do associate it with a command group using the handler object. So the buffer is not associated with any device yet, but the accessor is because of this command group. So you submit to a specific device, and that binds it to that device submission. So this is part of the scheduler, the scheduling that was mentioned before. The accessors dictate how these data dependencies are set up. And then the SYCL runtime can schedule operations based on these data dependencies. So that also means that it will allocate and copy data to any devices that it needs to, but only if it's necessary. Like if the, for example, if you request access to a device, then it might need to allocate and copy the data to that device. But then if you access it again on the same device, then it doesn't need to do any copies. So this slightly depends on the implementation, on how much it's able to optimize different accesses, but there are also certain guarantees by the SYCL spec on when allocations will happen and when they won't. So the data will then remain in the device memory after the kernel is finished until you have another command group request access on a different device. The same also happens, well, not the same, but if you destroy a buffer object, it will wait for any work that was submitted using that data. It will wait for that work to complete, and then it will copy back to the original host memory that we provided in this example. A quick look at the buffer class gives us the main information here that it has a data type, and it has a number of dimensions to represent the data. The buffer class also has an allocator that's not specified here. That's for more advanced usage. But this is what you mainly need to know, that it has some data and has a number of dimensions to represent this data. You construct a buffer. In this example, the simplest example, you have like you have a variable. You specify a pointer to this variable and also a range. Because this is a pointer, you can also have a larger range. But in this case, we just say it's a single variable, so we just need a range of 1. What's nice here in SYCL 2020 is that because of class templates argument deduction, we don't need to specify the dimensionality or the data type, because it can all be inferred from the the variable here and also from the range. We can see that it's a one-dimensional range. So as mentioned, there are different ways to construct an accessor because there are different types of accessors. So this is still mostly refers to SQL one-to-one terms, but it's pretty much the same in SQL 2020. SQL 2020, just the names are slightly different. The accessor has an element type and a number of dimensions. So this is the same as the buffer. And then it also has the access mode and the access target. So this is what's interesting here is the access mode can be read, write. So a SQL one-to-one was also discard modes or atomic. This was like a change in 2020 that instead of a discard mode, you just use the no init property. So this basically tells you, this sets the dependencies for the scheduler. It says that if you create an accessor with an access mode read, then the SQL runtime will know that that buffer is only accessed to be read. It won't be written to. And this can be quite useful then for managing the dependencies and determining which copies to perform and which can be skipped. Another template parameter here is the access target. And this specifies what you want to target in terms of the, usually, for example, like the device, you would specify either the host buffer, global buffer, constant. Again, slightly outdated here because of SQL one-to-one, but global buffer or SQL 2020, that would be just the device. Basically says that this is, you want access to data on the device. There are different kinds of accessors that we're not going to go into in this section, but there are other options that you can use. And the placeholder, so this has been changed again a little bit in SQL 2020. So here was a template parameter. This basically just allows you to not bind the accessor with a command group immediately. In SQL 2020, this is simplified so that you don't need a template parameter anymore. That pretty much any accessor can be a placeholder. Yeah, so here are some cases on how you might use the accessor class. This would be based on the access targets that I mentioned before. But yeah, we're going to only focus on accessing data on the device. You can construct an accessor by just using a buffer and a command group handler. And this also benefits from class template argument deduction in SQL 2020, that you don't need to specify any of those template parameters that we talked about, because it's going to use the data type and the number of dimensions from the buffer. It has a default access target, which would be global buffer or device, and a default access mode, which is read-write. If you want to optimize this a little bit, you can specify the access mode. You can do this via a deduction tag. So here you create an accessor with the SQL read-only tag, and that will create a read-only accessor. And the same for a write-only tag. You can also say that you don't want to, you want to discard the original data of the buffer. So if there was already any data before in the buffer, with this accessor, you just say that you're not interested in that data, and it can be discarded. So the access modes, so yeah, basically that if we have a read accessor, it's only going to read the data, and you cannot write to it in a SQL kernel. If you have a write accessor, you're going to modify the data, which creates extra dependencies. And the no init deduction tag as mentioned, it removes the dependencies on the previous command groups. There are different rules on how access modes are resolved. So in case you have multiple accessors to the same buffer in a command group, basically it means that if you create a read mode accessor and a write mode accessor, then it's going to be a read-write accessor. And the rules for no inits are that basically all the accessors need to have the no init attribute in order for the data to actually be discarded. If you have one accessor that's to the same buffer that doesn't have that, then you cannot discard the data. So if you do create multiple accessors, you can use them in the kernel, potentially in different ways, because you will not be able to write to a read-only accessor. But with a write accessor, you will be able to write it. So the resolution here just means that it's going to, for the purpose of the scheduler, it's going to resolve to read-write. And then you'll be able to use them in the kernel to alias to the same memory address, just in different ways. So this example, what was discussed before, that we have one read, one write. So the SQL runtime will treat this as a read-write access, but then in the kernel you'll only be able to use to only read from this one, and then but you can also write to this one. There's also the subscript operator to allow you to use the accessor more like a pointer to access the data. Here we've created a few accessors, two read-only ones and one write-only one. We read from these two, add the results, and write it back into the out accessor here. And yeah, we've accessed this using the subscript operator. And this can take, so this can be, so this can be a size T or it can be an ID class. So that mostly covers the buffer accessor model. And then now we can move on to USM. So unified shared memory is slightly different. That it requires a little bit more control. It exposes the raw pointers. You basically perform an allocation, you get back a pointer, and then you can use that pointer directly without dealing with buffers and accessors. It has its own advantages and disadvantages compared to the buffer accessor type. So we'll explore a little bit on how this works. You can perform different allocations. You can do a host, a device, or a shared memory allocation. This basically just means where the data will be allocated and where it's going to be accessible. We're going to focus on explicit USM here with shared and device allocations, but we'll discuss the others a little bit. So yeah, so if you imagine a bit more precisely on how this generally works, for example, if you have a GPU, it has its own memory, which is separate from the main CPU memory. So if you want to use memory on the GPU from the CPU, what you need to do is you need to allocate some memory here. You copy your data from the CPU into the GPU, and then you can do some calculations on it. And after you're done, you need to copy it back. So this might be a bit of a bottleneck sometimes. So you want to try to minimize these transfers. So the USM model basically exposes this a bit more explicitly compared to the buffer accessor model, where you have automatic dependency management. So if we look at different USM allocation types, so this is basically the kind of allocation that you perform, and it means that if you do a device allocation, is going to be located on the device and only accessible on the device, but not on the host. So we're going to focus on the device and shared ones, and the shared ones basically mean that you can allocate a short allocation, and then you can migrate between host and device. So this is an example of a device allocation that you call malloc device, which allocates the specified region of memory on the device and associates it with a specified queue. And you get back a pointer, which is only available inside kernel functions. So you can only access it while running kernels for the specific device. So you'll need to submit a command group to this queue that's associated with this pointer. There's also different ways, like if the device doesn't support this, if it doesn't have the appropriate aspect, then you're going to get a synchronous exception. This whole allocation is a blocking operation, and if you're familiar with CUDA, it usually would map to a CUDA malloc call. For example, I think this is specific to the DPC++ CUDA backend. But if you're familiar with it, then this is kind of what it does. For a shared allocation, it's similar to the device allocation in terms of that it's associated with a specific queue, but the pointer that you get is accessible both in host code as well as device code for this device attached to the queue. And again, if we're taking a look at the DPC++ CUDA backend, this would be a CUDA malloc managed call. And this is a convenient API because you don't have to worry so much about what's accessible where, but it's potentially slower than using a device allocation. Because we've performed an explicit allocation, we also need to explicitly free the memory once we're done with it. What's special here is that we need to use the same queue that we used initially to allocate the memory. And this is also a blocking operation. And then we have different operations that help us with managing the data. This is a memcopy. Most of the operations here are modeled on like standard C++ calls. So the API tries to resemble that a bit more closely. So you can use memcopy to copy from a user device allocation to the host or vice versa. And this is an asynchronous operation that's enqueued to the queue that you use. How do you know it's asynchronous? Is because it returns an event that you can then later wait on. Or it also takes a vector of events that you can pass into. So it's only going to perform the copy once all of these events are done. Similar operations are memset and fill. You're probably familiar with these operations in terms of C++, that you can set the memory or you can fill it with a specific pattern. And it has some of the same quirks. For example, the memset interprets the data to be an unsigned char, even though it's specified as an int here. And the fill function initializes data with this recurrent pattern. And because they return an event, they're asynchronous. So I think that generally covers it. We have an exercise number 3, where we're going to implement a SQL application where we add 2 variables and return the result. And we're going to do this in 2 ways. The first way using the buffer accessor model, and the second way using the USM model.
Yeah, I'll post a link into the next instructions. All right.
Hi, may I ask something?
Sure.
So the kernel execution we said before that is asynchronous. So if after the kernel we have a mem copy from the device back to the host, do we still need to have a wait for the event, for the kernel execution event, I mean? Or it's similar to CUDA that it knows that it has to wait for the kernel before it transfers the data back to the host from the device?
So in the USM model, you generally need to do the synchronization yourself. You can use events to pass between operations to set this dependency, to set the dependencies. Although there's also an option of having an in-order queue where everything is going to execute in order, so you won't have to worry about these when one operation finishes and the other starts. Yeah, generally you're going to have to do the synchronization yourself.
Okay.
Peter, maybe I missed something about USM. Is there any way to share the data between the devices directly, or it should be done only by a host? If the question makes sense at all, I'm not sure.
Yes. I guess that depends on whether data can be shared directly between devices. Usually, if they're on the same context, then it would be they would be usually able to see each other's data. If they're not on the same context, then it depends on the implementation more. That there might be a way to perform a copy directly, or the safest way is usually to go through the host, I suppose. Although I think there's been discussion also that the API might be a bit lacking in some cases for doing device-to-device copies.
Yeah,
I suppose if you have like a special link between devices that allows you to bypass the host, I don't think SYCL exposes that.
There's a couple of questions in the Slack as well there. That's Peter about using pointers and.
Yeah, I think it's very related to this question, requests. So it's actually, let's say, when you have a sub-devices, right? You actually can allocate the memory, at least in DP C++ implementation, you can allocate the memory and use these pointers in different queues in that case. But it's something specific to sub-devices we have. So that's why this kind of stuff is already relaxed a bit in some implementations, which Alexander is asking about.
Igor, and what do you mean by sub-devices?
Yeah, I think it's Intel extension we have right now, so that you can actually have a root device, right? And some device may have several sub-parcels, let's say tiles, right? And each of these tiles may be treated by a separate device on the software layer, but actually physically it's like same discrete GPU, right? So for this kind of configuration, the way how we are programming is we're creating sub-devices based on the root device pointer. So it's
okay, clear. I thought it's something like
in
the same system we have Intel FPGA and Intel GPU.
No. It's different device. It's like if some parts of your it's actually a quite useful feature not only for GPU. So if you want to play a bit with some kind of affinity on CPU, so you can actually allocate the parts of your cores as one sub-device and the other. So if you want a pointer, we have an extension on that, and we have a description of that in our GitHub project. But it's not yet in the SYCL standard. That's the point. So I think that there will be work, upcoming work, SYCL committee on that for the future. But at this moment, I don't think it's possible with SYCL 2020.
Okay, but at least it's good to know that something like that exists already. Thanks.
Yeah, it's happening, and again, I can put. I think I will answer to Alexander in the Slack with a pointer to this stuff.
There's a question about USM as well, and whether it's only for GPUs, but I'm trying to think if there are, I mean, obviously it can be implemented for anything, but are there any devices where USM is implemented that aren't GPUs at the moment?
CPUs.
Oh, CPUs, right? Yeah, sure. Sure.
And FPGAs too. I mean, USM doesn't mean that you have really shared memory at the same time. It can be just a ping pong between the devices every time you want to use your shared memory, for example.
But yeah, with explicit USM, you could potentially just have only support device allocations, which basically means that you get like a fixed pointer that you know is not going to change, and you can use that pointer directly. Yeah, for example, one limitation in OpenCL is that it doesn't guarantee that the CL mem object is going to be the same always, even though it usually is, like if you use it on multiple invocations. So that could potentially already be, in a sense, a USM pointer if you use it directly. I think that most implementations do that, but it's not guaranteed by the OpenCL spec. Whereas USM, you get the pointer directly that you know is going to be the same.
I don't know if you can hear me.
Yeah.
So okay, yeah. So I was just curious that in a scenario that you have a code which kind of ping pongs between the CPU and GPU, a kind of a mixed load work, then you've done a USM for it. But still the memories have to pass through PCIe transfers. So what is the specific advantage of USM? Does it have any advantage in that case, or myself should I manually manage it? How the memory is transferred, how much of the data is transferred between the two devices? I don't know if I explained it in the correct way.
I mean, yeah, it's not only about transferring data. It's also about having some data structures using pointers that might have a valid semantics on both host and both device. For example, if you have some graph algorithm, and then it provides some things that you cannot easily express with buffer except by using some smart pointers or something like that. But with USM, you can really have two pointers that point to the right thing between host and device.
Right, and then transfer that across the code. Okay, share that across the code. Okay, got it.
And note that actually, since it's GPU programming, right, benefit you're getting depends on transfer cost and the compute power, right, of GPU. So finally, transfer cost matter, and with USM you have more, I think, more explicit way to control the moments where you want to transfer the data, right? So you can actually minimize manually the moment. So if you want to keep the data on GPU and avoid additional copy back to CPU, you can do it explicitly with USM. While with buffer accessor mode, yeah, it's you also have some hints, right? But here it's more explicit and you have more explicit control over that. So
in case of integrated GPUs, will it actually have any benefit in terms of not transferring data between the two, just using one part of the memory and sharing between the CPU and GPU?
Yeah, with integrated GPU, there is no, so it's you're winning because the tax for data transfer is close to zero, right? So it's obviously good, but integrated GPU is not so powerful, so you're winning. So I would say that I've already seen some examples of workloads where usage of integrated GPUs really makes sense, right? Then you don't need these powerful discrete GPUs, and you just need to avoid this costly data transfer through PCI bus. That's really makes sense, but it's not, let's say, common in HPC. It's in some other domains.
Yeah, I agree. But there are some workloads that are memory intensive, so they might use that. It's a curious thing to check. Yeah, thank you.
I guess it depends on the device as well. For some devices, it might be more efficient to use the buffer accessor model. But like, I guess as always with performance, it's you need to benchmark. Another advantage that USM might have is porting existing codes, like either like CPU code or potentially CUDA code where you just have pointers, and trying to adapt that to the buffer accessor model might be quite a lot of work. Whereas with USM, you just use the existing pointers and like just plumb the existing functions into kernels.
Yeah, compatibility with other models is quite important stuff here. So, for example, in our Intel implementation, there is a way how to mix SYCL code with OpenMP code, and you can even reuse the memory which is allocated via USM, right? But if you're doing it with buffer accessors, it will be not possible to do. So that's another way how to think about it. And then definitely USM APIs better map to CUDA corresponding APIs. From that point of view, it's easy to migrate some code.
Okay, that makes sense. Thank you for the answers.
All right, welcome back, everybody. Hopefully, lots of you managed to get the buffers and USM stuff working and now understand how that works from a practical point of view. I think just double checking. Yeah, it looks like we have lots of people available now waiting for the next session, so let's crack on with that. Quite a lot to cover for the rest of the tutorial today. So this is, I guess, a slightly more advanced topic, ND range kernels, as opposed to some of the earlier sections in the SYCL Academy main materials, but it kind of focuses on this as it's quite a useful thing to understand if you're going to be writing some SYCL code. So I'll let Ronan jump in and start talking about that. Thanks, Ronan. Oh, I think you're muted.
And now?
That's better, yeah.
Okay, thank you. Yeah, so let's talk about some more detailed subject. The idea here is to learn more about how SQL works on the execution point of view and how the memory models work. And then we will learn with some exercise how to enqueue some specific kernels. We will see the ND range kernels. So the execution.
We can't see your screen, by the way. That's better, perfect.
Sorry about that. Yeah, so that's what you missed. So the execution model is based on work items that allows you to execute the kernel functions. And you can think on the CPU that this work item would be a thread or a fiber. And each work item will execute an instance of your SYCL kernel function from the start to the end. And if you have a CPU device, so it could be besides the thread or the fibers, it could be single lane, but on GPU, it will be probably some threads or whatever. If you have FPGAs, can be implemented in hardware. But since there are a lot of parallelism in accelerators, so there are usually different level of hierarchy in your work organization and the architecture organization. So that's why these work items are in SYCL collected together into a work group. And the size of the work group itself has some impact on how the things are executed, and you might try different sizes for your application to optimize your performance. And of course, in some cases, how it is concretely compiled or executed might limit, for example, the work group size because you lack registers on the GPU or something like that. And you can even have several work groups, and that's what why you can arrange them together into some range of work group. And since we are able to have multidimensional arrangement, that's why we have this concept of ND range or n-dimensional ranges. So each ND range has a number of work groups, and inside each of them you have a number of work items. And the work groups in the current version of SYCL have always the same number of work items. That's what we call uniform work group. And if we look deeper, if you look deeper into the ND range organization, they are composed into according to 1 or 2 or 3 dimensions in the current specification. And what is important about the ND range is a global range that describes the total number of work items in each dimension. And inside each work group, we have the local range here that describes the number of work items in each dimension. So each invocation of a work item inside this ND range will have some coordinates so that you can really know where you are in this space. And so that's why you have a lot of specific functions in SYCL to get all these coordinates. So we've seen already the global range. So it's here it's 12 by 12. But if we look at a specific work item, here we will have the global ID 6 and 5 here. We have a group range, which is the number of ranges into your inside your ND range. So it's here it's 3 by 3, and you can also number your group. So here we have a group ID, the group coordinate. So it's a 1, 1, and the local range, as we've already seen, it's 4 by 4. And inside the work group, the local ID is 2, 1. So with that, you can organize your work. And all these work items are executed in your accelerators to execute the SYCL kernel. And typically for big accelerators, you might have thousands of work items working concurrently to solve your problem. The details actually on how the work items are executed together or in respect to each other is actually not specified in the standard. So that's why in SYCL you can actually target a lot of different accelerators with different execution details. For example, if you have some vector hardware, you might have some SIMD instructions executing several work items at the same time in a lockstep way. And actually the number of work items that will execute in parallel will vary from one device to another, or even during the current program execution according to the current execution phase. And typically your system will batch together different work items in an unspecified way, and to execute them in the same work group. Or you can also even have a different work item from different work groups executed all together. But at the end, what you need to remember is that it's up to the implementation. So you should not rely on any specific execution order to have your algorithm working. Another feature we have in SYCL is the concept of a barrier, which is a way to synchronize all the work items in a work group in a way that, for example, here the barrier in red will block all the work items thread of your work group up to the point that they all arrive, and then they can go on their execution. If you have a different work group, actually there is no support in SYCL to have some barriers across work group. So if you really want to have an execution in different phases in your application across all your work group, the only way to do the only simple way to do it is to have one first kernel executing up to completion, and then you will start another kernel once the previous is executed. You could do some more complex stuff by using atomics and things like that, but or reduction, but that's outside of this introduction topic. So when we have seen the execution model, we can look at the memory model, which is about how you will store your data and how you will access them. The simpler memory we have in SYCL is the concept of private memory, where a work item can just access its own private memory. So it cannot access the private memory of another work item. And we have another hierarchy, which is a local memory, which can be accessed by any work item inside the work group. And a work item in a work group cannot access the local memory of another work group. And we have at the end the concept of global memory, which is accessible by all the work items of the ND range. And in some cases, you have, for some backends, the constant memory, for example, in OpenCL, but it's not a requirement in SYCL 2020. So why we have all these different levels of memory is that because they all provide you different trade-off between size and cost and speed. And so the global memory is shared by everybody, and it's usually very big. But it's far away from each work item execution unit, so it might be not that efficient. The local memory is smaller, but closer to the work items of the work group, so you can have quite better performance, so you can use it typically as a cache to share some information between the work items of your work group. And there is this private memory, which is the fastest probably in your architectures, which is typically implemented as registers in FPGAs or GPUs, and that's what you can use if you do not need to share anything with the other work item in your system. So now we've seen how the computation can be organized in work items and how you can define variables in different memory levels. Now we will see how you can express parallelism in SYCL. So if you want to create several work items working on your problem, you use a parallel for member function, and there are actually different overload of these member functions according to whether you want to expose a lot of details of how the computation is organized. If you are not really interested in details, you can just use a parallel for taking some ranges and executing a kernel defined as a lambda taking an ID, and then it will launch your kernel on all your work items into your range here, so 1024, and inside your kernel you will have the ID defined to the current work item. So there is no actual concept of a local range here. So perhaps there are behind the scene, but it's up to the runtime to decide how the computation will be organized. There is another overload for parallel for taking a kernel function, taking an item, and with this item compared to the ID, you have inside the item and also the the range of the global range that you can use in it. So you have more information. And the last overload here is just to use to be able to precise the global range and the local range of your ND range iteration space. And then the kernel function will take an ND item that will expose quite more details. For example, you will have you will be able to get the local ID of your work item, or the you will be able to introspect in which work group you are and things like that. After that, you can use some global buffer from the global memory by using accessors, and there are different ways to do that. So you can access the subscript operator directly with an ID, and then there will be a direct mapping between the work item ID and how the accessors is laid out in memory. But you could also use the nest subscript operators, like in a multidimensional C array, where if you have an accessor with 3 dimensions, you will have, you can use XYZ, or you can also get a pointer from the accessors and then use it like any pointer in C++. So just to give you an example, so here we have 3 one-dimensional buffers, and you just have a simple parallel for taking range and launching a kernel taking an ID, and then you can directly index all the accessors with this ID. But we could decide that instead, inside our kernel, we will get the pointer to the accessors pointing to the buffers. And we can use the get linear ID function to get a linearized ID from the 3D down to the 1D according to a row major order, which is the normal C++ way to linearize arrays. And then you can just index your pointers as in normal C++ with this linear ID, which is a size t. So I don't know if you have some questions before looking at the exercise.
And I have a question. I didn't get clear understanding between the item and ID. Both of them are within a global range. But if you can maybe just tell the use cases when it's just recommended to use just ID and in parallel for, and when it's recommended to use the item, just maybe briefly use cases for that. I know it's just quite similar. The previous one, when you have three parallel force, one is ID, the second is item, and the third one is in the range. Yeah, that's it.
Yeah, so it depends on your algorithm. If you do not really care about any optimization, for example, you just want to do some matrix addition, so there is no locality you can exploit in the algorithm. So typically you will just have a very simple kernel, just taking an ID and reading the B and C element and writing C. So that's a simple case. But if you, for example, want to do some matrix multiplication or convolution, then you will have n square access to the global memory, but you have n3 multiplication to do the matrix multiplication by block. And then that means that to exploit this, you can, for example, use this yellow work item, so my work group, as a submatrix computation. So they will first load all the submatrices from my global address space into my local memory, and then you will use your local ID to just read all your submatrix elements and do the matrix multiplication locally for this small block. And then you will get some other pieces from the global memory by using the group range and the group ID to compute another block and things like that. So if you want to exploit the locality of your memory access and do this kind of tricks, you need to enter into these optimizations. So that's typically the use cases.
Yeah, thank you, clear.
Any other question?
I had a question on the implementation side of it. So in case of CPU, for example, then you have SIMD and threading. When you are creating that parallel for, is it important that these work items are actually equal to each other, or how does a compiler know where to put it in a SIMD, where to put it in a threading? Is it can we have microcontrol over that, or this is something that the runtime will decide?
That's a good question. It depends on the implementation. I know that typically, if you could have a CPU implementation of this execution model based on OpenMP, so you will use a Pragma SIMD from OpenMP to just say, okay, I want all my work items into SIMD operations. But you might have some other implementations. For example, I know that SYCL has probably something more similar to what you think about what you have your microcontroller, but it's in the runtime, which is when you have barriers. I think that SYCL runtime decides to create some fibers to execute independently all the different work items more independently on the CPU side, because there will be more things happening in parallel, independently. So it's a difficult question to find automatically the right execution model on CPU. So up to now, it's up to the implementation. So in SYCL, it is implemented with threads, which is or fibers, which is rather inefficient. But you could have some compiler looking at the code and deciding that, yeah, it's okay to automatically vectorize your code because you do some nice dependence analysis in your code. And if it's safe, yes, you can execute everything in parallel. So the problem is that when you cannot decide that at compile time, well, it might be less efficient on CPU.
Is it possible to know actually which work item has been implemented in what way after the compilation?
Yes, that's a good question, but I think it's not that different from a current compiler where you execute some for loops and you don't know whether which one has been vectorized or not, but you can ask your compiler by using the right flag so that it can say, oh, I've parallelized these loops and it is executed in SIMD, for example. And at the end, well, you can always look at the source code or use your debugger tools or profiling tools that will probably show you that it is vectorized and things like that.
Okay, thank you.
Okay, so if there is no other question, then we can switch to the exercise. And I think that Rod has sent the link to the Slack channel. The idea is to play with the various version of ND range and execution using either ID or item in parallel for, or using ND range when you ensure your kernels, and then you can play with the various functions available there. If you are curious about all the member functions that does exist in the ND item and things like that, you can look either at the SYCL reference guide or the SYCL specification. Oh yeah, but you can play with is either use streams to display some function you are interested in. You want to see how it is implemented, or you could write some values of get global ID directly into some global buffer and look at what you get and things like that. We don't have a specific problem to solve here, it's just to understand how it works. Yes, so in this small snippet, so they just create some buffers to wrap some existing array which are initialized globally here. And then we launch here some one-dimensional ND item, and here it's a super simple use case, a minimal one, where you just get the global ID of your ND item, and then you just use your accessors by using this get global ID. So it's really a minimalistic use case, but you could do some more complex computation or doing perhaps some initialization, including some local ID or whatever. But it's just an open exercise, so this is just a simpler possibility here.
Thanks, Ronan. All right. I guess I haven't heard from anyone specifically about getting more time, so that gives us a bit more time to talk about the next section, which is the final part of the tutorial today that Peter's going to cover, which is again try to do things a little bit differently this time, but it's an image convolution, which is quite a simple image compilation, but we're sort of treating this as a bit of a case study. So Peter's going to do a little presentation on kind of how this is done, and then he'll spend some time walking through the code and helping you to understand how it's been implemented with SYCL, so that can help you maybe get it straight in your head how you might do something like that yourself. So Peter, are you ready to go?
Oh, yes.
Perfect. Great.
I'm ready. Right. I'm going to start sharing my screen. That should be it.
Yep, you can see that. Perfect.
Okay. So I guess this section is a bit more advanced SYCL, but it depends on how much time we actually get. So we will be looking at the slides a little bit. So the IWOCL 22 branch of the SYCL Academy only has these slides that I'm going to show right here, which is explains image convolution, and we're going to go through the codes. But then if we have time, we can take a look at the other lectures from the main branch, which also go into like optimizations we could do for this. Yeah, so we're going to learn about image convolutions, why this is a good problem for solving on a GPU, and we're going to look at the naive convolution algorithm. Yeah, so this is a good motivational example because it's good to solve on a GPU. There are multiple optimizations we could use. There are many applications of this. For example, deep neural networks and image processing use this quite a lot. And the reason why this is so good to execute on a GPU, or I suppose any other similar heterogeneous device, is that the algorithm is embarrassingly parallel. So each work item in the computation can be calculated completely independently. And you perform a large number of operations for each work item, especially if you use large filters, and it requires a lot of bandwidth. A lot of the data has to pass through the GPU to process the image, especially with higher resolutions. So this is to give you a mathematical overview. So some of you probably already know about this, how this works. But basically, we have our image represented as numbers, and we apply a filter to each pixel, basically. What we do here is that we take the surrounding area of the pixel, multiply it with a filter, add all the results, and then we get a single number back. And in this case, this is a Gaussian blur. So this blurs the area of the pixel. And then in the end, it blurs the entire image. So this is an example of how the transformation happens. So we're going to take a look at what we need for this. We're going to write a convolution kernel that performs the actual convolution. We're going to need an input image and a filter. So here, the blue boxes indicate host data. And then we need to copy that to the GPU. Or in the case, once we get the output image, we need to copy it back to the host. And we're going to read, but not write to these inputs, and the output we're going to write to, but we can leave the initial data uninitialized. So there's a naive implementation inside the repo, and this is going to be the basis for optimizations. If we get to that, we use the STB image library to help us visualize our results, and it's possible to benchmark what we have, so we can measure the performance. You've already seen the reference image. This is in the images folder. You can use your own image, but this is probably the easiest to set up. Yeah, so we're going to use these images. If you use something else, then be sure to update it. And we have a utility function to generate the filter based on the type and the width. We have a look at the performance. Basically, the larger the filter, the longer it takes to perform the computation, because we're doing more operations, of course. And at this point, are there any questions? Right. If there are no questions, then we're going to take a look at the codes, which I have in here. So this is in the image convolution. This is the reference code. So let's step through it. What's going on here? There's a little bit of setup. Of course, we have to include the SYCL header. Here, you're probably familiar with this now. This is a forward declaration of a class that we don't actually use, but it's used for the kernel name. We set up some constants that we're going to use, and then we have our test case with the input and output image. We can read the image, allocate it based on the requirements. Similarly, we can set up the filter. So this is all host data, right? And then we go into the main SYCL code. So we create a queue. We say that we want this to execute on GPU. We can change it to something else if we have a different device. But here what we say is that we also say that if there are any exceptions encountered, any asynchronous exceptions, they're just going to be dethroned. And we can then catch them at the point when we do a wait and throw. We display some information about the device, the device name. And then we go into creating the SYCL ranges. So for the global range, we set the image dimensions. For the local range, we're going to go with 32 and 1, just to, I guess, simplify it for now. We need to calculate how much we're actually going to need to store in our buffers, because we need to reserve a little bit for our halo. So if you remember what I showed you, that we're going to use the area around each pixel, which means that the entire image is going to have a halo that we need to account for. So this is a calculation for how much data we actually need to store. And then we can create the buffers. From our input image, we create our input buffer. From our output, so here we dedicate some data for the output image. Here we don't pass a pointer to any data. So that means that also that class template argument deduction is not going to work, so we need to specify the template parameters. And for the filter, we also create a buffer from the filter data and the range. And then we also set for this output that we created, because we didn't associate it with any pointer. Right, can you see the code now?
Yeah, we can, yeah.
Okay. I think I got cut off when I was discussing the accessors, right?
Yeah, that's right, yeah.
Okay, right. So let's get back to it. Okay, so here we can see that we request access to the data. So this is to inform the scheduler that the SQL runtime that we're going to use the data in a specific way. We're going to only read from the inputs, and we're the same for the filter, but we're going to write to the output buffer. Then we can launch our kernel, our image convolution kernel. We specify the end range we want to use. And because we use the end range overload, then we need the end item here. We can retrieve the global ID from the item. We do some calculation on what we actually want to access. So we take the global ID, add the halo, and multiply that by the number of channels, because we use 4 channels for each pixels. Similarly for the destination, that we take the global ID and multiply that by the number of channels. For the sum, we initialize it with all zeros, and then we basically iterate across the filter. So yes, we calculate the offsets for each of these. Same, we calculate the filter offsets, and then for each of these channels, we multiply the inputs with the filter, and then we sum everything into this array, so for each pixel, and then we write out this sum into the output image. So that's basically it. That's how the simple convolution works. So after that, we submitted this work, so then we need to wait for it. Waiting throw will, as I mentioned, if there were any asynchronous errors, they're going to be raised at this point, and then we can catch them if needed. And because this is using buffers, is because when this buffer goes out of scope, this outbuff is going to copy the data back to the host, to this pointer that we specified, and then we can just write our image. Are there any questions about this code? No.
No.
I'm guessing some of you might have already seen something like this. Oh, sorry, was there a question?
I was going to ask a question about, is it worth talking about sort of maybe work group size in the context of this, if nobody has any questions?
Yeah, sure.
In terms of figuring out what work group size you might choose.
Yes, so that's one possible tweak that we could do. Because here we said, so for the global range, we specify whatever the dimensions of our image are. But then we could specify a different local range. So here we just went with 32.1. But we could potentially like benchmark this with different values to see what works best. Sometimes the device vendors might have a preferred value as well for the local range. So yeah, it's definitely worth playing around with this a little bit to see what gives you the best performance. Yeah, I guess if there are no questions, we could start looking at some of the optimizations that we could do.
Yeah, sounds good.
So I have, in addition to these slides, I have these from the main branch. So first thing we can take a look at is coalesce global memory. We're going to learn about all this. So as we all know, reading from and writing to global memory is quite expensive because of all the copying across an off-chip bus. But what also usually happens is that memory access operations are done in chunks. So if you access data that's physically close together in memory, that's more efficient. And we can take a look here. So for example, if we have an array of floats that's laid out in memory like this, and then we access each, we can say that each work item accesses one element of this array. So we have a direct mapping. So this is a very nice utilization, 100% perfect. So here we kind of show how data might be copied over to the device in chunks. Here we set that each chunk would be 4 elements, for example. So what happens then if you access this data slightly differently, so that each work item, instead of accessing the exact the memory that it would access it directly, instead we say ×2. So instead of accessing this, we access this one here. So instead of this is this, and so on. So we access every second memory object, and this leads to bad utilization because we still do the copies. Well, we don't do them, but usually the bus or the drivers do this, and they copy the data over in chunks. So we have the chunks of 4 here, then we copy over data that we don't use. This is in red, and we only have 50% utilization in this case. So this is especially important when you have data in multiple dimensions, because you need to convert from a 2D space to a linear memory space. There are 2 main ways. I suppose there are others as well, but the main ones are row major and column major. So for row major, basically the memory is laid out like this. So we go 0, 1, 2, 3, and then 4, 5, 6, 7, like this. And then with this access pattern, we get proper utilization, right? So this is SYCL defines buffer data to be row major because that follows C++ as well. But then if you try to access data differently in a column major fashion, then you get all scrambled data accesses, and then that's bad for the utilization as well. So you need to change the way you access the data as well. That you basically change the indexes here. And for example, in OpenCL, usually the data, the buffers are column major. The data is laid out in the column major fashion. So you would prefer to access the data in this way. Yeah, I guess what's important here about this 4 is that we changed it. Since this is square, it doesn't matter, but this 4 refers now to this height, I suppose. Similar problem is if you compose data structures, you typically want to represent them as a struct, and you have some data inside, and then you have an array of these structs. And this is referred to as an array of structs. But for data barrel architectures, it's better to have this stored more contiguously in memory. So you have a struct of arrays instead. We're going to demonstrate how this works. So you have, in this case, you have your struct. We store one float and one integer inside, and then we have an array of these structs. And then if we try to access in each work item, we just access, for example, first the float, and we see that we get the exact problem that we mentioned before about utilization. So only for 50%. And then we access the integer after this, and it's the same problem. So what you can do instead is lay out the memory so that we first have an array of floats. So you can see the F boxes here, and then an array of integers. So then when we access first the floats, we get perfect utilization. And then in the next step, we access the integers, and again, excellent utilization. And so for our image convolution, this can make quite a big difference. We can get quite a performance improvement if we take into account the coalesced memory accesses. Are there any questions about this? Okay, let's take a look at the code and see. Would anyone be able to tell me like what we need to do in this case to get the better utilization? Right. So I guess what we discussed is that SQL represents these buffers. So these are 2D buffers here that we're dealing with, and it represents them in a row major fashion. But if this is running on OpenCL, for example, the buffers there are going to be column major. So we're not going to get the optimal access. So what do we need to do to improve this? The solution here is actually quite simple because SYCL already performs a lot of the index calculations. So we basically just we can basically just say go by D1, go by D0. That should be it. We just switch how we access them. And this global ID is going to be used later on. We're still going to use all of them. The code is still correct, but we change which ones we access first. And that's it. That's how we get the performance improvements in the convolution benchmark. Right. Any questions? in that case, I suggest we continue, because there's another very interesting optimization that we could do here, and that's local memory. So again, global memory access is very expensive. And even with the coalesced memory access that we did in the previous exercise, we're still accessing the same elements multiple times. And if we have to fetch this from the global memory every time, then it's going to be very expensive. So we wanted to have a way to cache some of these values. So if we take a look at how convolution works, we said that each pixel uses a surrounding area. So it needs to, each pixel needs to read each of its neighbors. And then the second pixel also reads each of its neighbors. So it's reading the same values again. And this is especially problematic with larger filter sizes. Here for a 7x7 filter, that's up to 49 operations that are performed for each pixel. And if these are memory loads from global memory, this is very expensive. So what we instead do is that in this memory hierarchy that we have private memory that executes directly on the kernel. Well, not executes, but is located directly in the kernel, and then global memory. So if we need to access data, we need to go out into global memory and fetch it, bring it into our private memory. We can add local memory in between here. This is usually an on-chip memory. It's not quite a cache because you manage it manually, but it does have much lower latency than global memory because it's on chip. So it's usually a smaller dedicated region of memory for a work group. And we can use this to cache the values. So this is often referred to as a sketchpad as well. So in this case, the iteration space of the kernel function is mapped across multiple workgroups. Here, the example illustrates how this whole section might be one workgroup, and this is another workgroup. So in total, you have 4 different workgroups in this case. And each workgroup has its own region of local memory. So that's why we talk about tiling, because we want to split the input image into tiles. So each workgroup would be one tile. For this, we can create a local accessor. We do this with the local access targets, or in SQL 2020, it's preferable to use the local _ accessor data type. You specify a range to it, how large it should be, and usually, so you want this to match the size of the workgroup, the number of items per dimension for each workgroup, and also the command group handler. Yeah, so this is the range, is that the number of elements that you're going to allocate in local memory. And so you can use this local memory to share the partial results between work items. But you get into one issue here, that you need to be able to synchronize between writes and reads to memory, so that you ensure that all the work items have reached the same point in the program. So this is because work items are not guaranteed to all execute at the same time. So here we have some work items that write data to their own memory region. But then if you want to read the data from a different work group, so here, for example, if you would read from the neighbors of the pixel, you would get, here would work, but here you're crossing workgroup boundaries, and that would not work. So that creates a data race. So you need to synchronize. You need to create a workgroup barrier to synchronize the results. So the workgroup barrier, when you insert it, it will wait. The work items will work for the entire workgroup. So this wasn't across the workgroup. This was still in the same workgroup, but not everything is guaranteed to execute at the same time in the same workgroup, right? It's generally only the width of the SIMD unit, for example, that is going to execute in lockstep. So you need to synchronize that. And yeah, and only then when you synchronize, when you have the barrier, then you can continue with your execution. So yeah, I had to correct myself because you cannot synchronize this across workgroups. So for local memory, this is usually fine because you're only interested in the local memory, which is per workgroup, and you only want to synchronize that. And yeah, work items can only access their own local memory, not of other workgroups anyway. This is how you can create a barrier. You can get the group object from the ND item. And you can get some good results here as well. So this is compared to the vectorized version of the image convolution, which we didn't cover, but it's another option. But I'm not sure if we're going to have time for that. So yeah, are there any questions about this, about tiling and local memory? I see a comment about changing the channels from an array of structs. Sorry?
I was going to say there was a question on the Zoom, yeah.
Oh yeah. Yeah, so changing that from an array of structs to a struct of arrays would be more problematic, yes. I think that's quite an active area of academic research on how to do this in an automatic way, because yeah, it's not easy to do it.
Actually, in Intel, we have in the compiler we have a so-called STDL library, which help exactly to solve the same problem. So it's keeping your object-oriented style while under the hood changing the layout from AOS to SOA. SDLT library, which is the name of the library. It's quite interesting how it can help to solve these kind of issues.
Okay. Yeah, that sounds good. Yeah, I think I've read some papers on doing that like a few years ago, so it's good that it's available. So in DPC++, you would get this?
Yeah, that's a good question. It's actually a set of header files, right? So it's also implemented as a templated library. So theoretically, you can reuse it from classic compiler or Intel classic compilers. I haven't checked if it works with DPC++. Yeah, but it was a feature of our former compiler we had in the past, and which we still have in one API toolkits. So I think it can be reused. It's quite interesting. I will put a link just for your reference. It's interesting stuff.
Yeah, excellent.
That's great. Well, thanks, Peter, for spending all that time walking through those different possibilities. That was very interesting.
I mean, so there are more options, and I would suggest people take a look at that offline if you're interested.
Yeah, definitely. Yeah. I put a link into as I was talking about, the main branch for SYCL Academy and all the different sections that there are. I think there's maybe one or two, maybe one further optimization that is talked about for the image convolution, so definitely worth taking a look at that. But yeah, I guess we're bang on time pretty much. So unless there are any last minute questions from anyone, I'll give you an opportunity to jump in. Doesn't sound too much like it. That's all good. It might be late where you are, so thanks for staying with us. I'll just say thanks to the speakers that joined us today, Axel, Igor, Peter and Ronan. Thanks again for making this such an interesting tutorial, and thanks everyone for joining us. I hope that you managed to learn a few new things, and it's going to help you on your journey to developing better SQL code. We'll be on the Slack channel for the next, well, week or however long that IWOCL is going to last. So if you do think of any questions, or if you're working through any of the lessons or examples on the Academy project, then post your questions in there, and we'll be happy to try and answer them for sure. I'm sure we'll all be popping on there.